It's okay, Jayant. I think we can start.
Oh, yeah, it's a great pleasure to invite Professor Rajat Mittal today. This is the fifth in the series of distinguished speakers lecture. Um, Professor Rajat Mittal got his BTech in aerospace engineering from IIT Kanpur in 1989 and PhD from UIUC in 1995. He broadly works in the area of computational fluid mechanics and in particular application to several diverse areas, including biomedical engineering, biofluid mechanics, fluid structure interaction problems, and flow control. And he's been greatly honored he got the Francois Frankel Award of DFT in 1996 and two awards from ASME, Lewis Moody in 2006, and most recently the Freeman Scholar Award in 2021. He is a well-known computational fluid mechanician, and most recently I saw a paper by him where he gave a very nice overview of a lot of different aspects of fluid mechanics related to COVID. And of course, he's been working on this topic for a while now, I think. And he's in the editorial board of several journals, among them Journal of Computational Physics and Journal of Experimental Biology. So over to Professor Mittal.
All right, thanks, Jayant. I'm going to share my screen here. Actually, hold on one second. I believe. So can everybody see my presentation now in the presentation mode?
Yeah.
Okay, great. So I'll get started. So I'm going to talk today about two projects that we've kind of been working on almost now, I think now for about 7 or 8 years. These two projects seem kind of diverse, but hopefully I'll show you that there is some connection between beating hearts and buzzing wings. So let me get started. So just to kind of give you a bigger picture about the first topic that I'm going to talk about, which is the the fluid dynamics and kind of biomechanics of the heart. And what I'm showing here in the middle is a kind of a picture of the heart, of the human heart. It turns out that the human heart, just like all the organs in the body, but more so than other organs, is really a very rich substrate for multi-physics kind of computational modeling. And of course, fluid dynamics is at the center of the functioning of this organ in our body, this critical organ in our body. Of course, first and foremost, the heart is a pump. So we are, as mechanical engineers, pumps are pretty much central to everything, to kind of fluids engineering. So I think this is a very interesting kind of a research kind of area for anybody in fluid mechanics to get into. And I got into this about almost like 15 years ago, trying to apply all the tools that we had developed for kind of aerospace type of applications to these very interesting biomedical problems. So just to give you kind of an overall sense of the complexity and the richness of the problems involved in the heart. Of course, first of all, the flow inside the heart is at a round number. Adult human heart is anywhere around 4,000 to about 10,000. So this is a very interesting regime for flow. It is neither laminar nor is it higher Reynolds number turbulent. So it's actually a transitional flow, and transitional flows actually can be much more difficult to, in some ways, to model than either laminar or fully turbulent flows. So that complexity comes in. Of course, there's moving boundaries. The heart is beating, and you can see on the left-hand side an echocardiogram of a beating heart. And within this beating heart, there is also electromechanics. Of course, the muscle is contracting the heart, so electromechanics, the coupling, electrical activation and mechanics is important. Although I don't work in that area myself, but certainly a very interesting area in itself. But more so, kind of my interest lies in the intersection of fluid flow and fluid structure interaction. So again, on the top left, you can see the leaflets of the heart actually opening and closing as the heart is contracting and expanding. And that's the mitral valve leaflets that you see. And these leaflets open and close not due to any muscular action directly, but through the flow-induced pressure and other forces that are induced by the flow on the leaflets. So that's a kind of an interesting problem in itself. And then, of course, we are all very used to going to the doctor, and the doctor listens to our heart. And so, if underlying all that is, of course, the acoustics. And acoustics itself is a byproduct of the fluid flow and the movement of the valves that are intrinsic to the functioning of this organ. So heart acoustics is another field, and this is one field that really, we've done a lot of work in this. Today I won't get to talk about this, but this is a very interesting area of research, is how to take our understanding of fluid flow and really apply it to understanding the kinds of sounds that are created by the heart. And the final kind of multi-physics problem is the coupling between flow and chemistry, and biochemistry particularly, and the biochemistry of coagulation and thrombogenesis. Here again, I'm showing you, by the way, a lot of my talk is going to focus on what's called the left ventricle. So the human heart is a 4-chambered heart. You can see the 4 chambers, 2 on the top, 2 on the bottom. I'm going to focus, a lot of my work has focused on the left ventricle, which is the primary pump of the heart. It is the most energetic, most powerful component of this heart pump. And it's most prone to all kinds of diseases and malfunctions. So on the lower right, you're seeing actually the left ventricle of a person. And this person has a very large blood clot sitting at the bottom, at the apex of the left ventricle. And how this clot forms, it turns out the clot formation is driven not only by the biochemistry, but the biochemistry itself is being modulated by the fluid dynamics inside the heart. So that, again, turns out to be a very, very interesting problem. And I'll spend quite a bit of time. The first part of my talk is actually totally focused on this whole connection between fluid dynamics and biochemistry. So again, lots and lots of interesting problems for anybody interested in computational physics, in computational fluid dynamics, and all the coupling between fluid dynamics and structures and chemistry and acoustics. So I'll jump right into kind of the first part of the talk, which is on blood clots in the heart. So clot formation, as we all know, clot formation is, if you take blood tends to coagulate very quickly if you keep it stagnant, right? If a drop of blood falls on a surface, it coagulates very quickly. So we know that stagnation is a recipe for coagulation. So clot formation is directly connected with flow stasis or flow stagnation. And it turns out that our natural healthy cardiovascular system, especially the left ventricle, is very good at ensuring that no clots could form inside the heart. So here I'm showing kind of the movement of the entire heart based on a CT scan. You can see the left ventricle expanding and contracting. And it turns out that a normal left ventricle will expand and contract in such a way that it produces about an ejection fraction of about 55%. Ejection fraction is the ratio of how much blood is pumped out in every stroke to the total diastolic, the final volume of the left ventricle. So this number is a very critical number. This ejection fraction, or EF, as it's called in medical circles, is a very critical parameter of the functioning of the heart. And for normal healthy hearts, ejection fraction is 55%. Now, this number seems a little bit on the lower side, that why would the heart not pump out more than 55% of its volume? Of course, it would be nice to get more blood kind of supplied to the rest of our body. But it turns out 55% is kind of been optimized as an optimal point between the contraction of the muscle, the kind of the efficiency of the muscle, and also kind of the fluid dynamics and the dissipation of flow in the heart. And it turns out that despite this relatively low ejection fraction, which is only 55% of the blood leaving the heart is beautifully designed to produce this kind of sweeping flow. The flow comes in from the outer wall, near the outer wall, and then goes out through the inner wall. And in doing that, it kind of sweeps the entire kind of the this left ventricle so that there are no pockets of stagnation left inside where blood clots could be formed. So that's how a normal heart works. But of course, if somebody suffers from a myocardial infarction or what's called a heart attack, or from heart failure or different types of arrhythmias or cardiomyopathies, then of course the functioning of the heart is compromised. And those are the kind of diseases where the patient can end up with what we call a left ventricular thrombus. So again, this is a similar picture of the left ventricle showing a big blood clot sitting at the bottom of the heart. So the question, so first of all, what are these clots actually? These clots are very interesting structures in themselves. So the clot is actually a normal, in some sense, it's a normal part of our body's process to stop or repair damage to tissue. If you cut yourself, of course, you want the blood to clot very quickly, and the clot will, hopefully, if everything's functioning okay, your blood should clot very quickly and stop the bleeding. And the repair of the tissue begins right after the clotting. So the clotting is a very key part of our ability to stay healthy, except that in the wrong times, it actually leads to clot formations where clots are not needed. And that's kind of what's happening in the left ventricle. So what are clots made up of? Clots are almost like a brick and mortar type of a construction. So the bricks are actually the platelets. So the yellow cells that you see are platelets. Platelets actually circulate in our blood. And these are the key factors in the clot. And then there is kind of a binding agent, kind of like the cement or the mortar, which is the fibrin. So these are fibrin or long chain molecules, and these long chain molecules kind of tie these platelets together. So it's a very beautiful structural kind of construct that is created. And so think of this as a little patch that will start to form on any place that is damaged. And basically what is happening is that somebody who suffers from myocardial infarction or heart failure, etc., their tissue actually is kind of damaged. So that is the starting point of the clot formation, is that the tissue gets damaged a little bit, and the body thinks that it needs to repair that tissue, and that's how the clot formation begins. But then the clot formation can be accelerated due to the stagnant flow that is created in a compromised heart. So the issue is that, okay, if there's a clot forming in the left ventricle, what's the problem? Okay, there's a clot there, so big deal. It's sitting at the bottom. Does it really cause a problem? It turns out that the problem is not that if the clot keeps sitting where it is. The problem happens is that these clots tend to be very unstable, and small pieces of these clots can actually break up and break off. And then when they break off, they can actually travel downstream. And you can see in this little graphic, a blood clot that is moving down an artery. And of course, at some point, it's going to encounter an artery which is too small for it, right? Arteries continue to branch and become smaller and smaller. So at some point, this blood clot is going to reach an artery that is too small for it to go through, and it is going to block that artery. And once it's blocked that artery, that leads to what is called an embolism. And it can lead to a stroke if it blocks an artery that is heading towards the head, or if the artery is actually the artery that supplies blood to the heart itself, it can cause another myocardial infarction. It can lead to another heart attack. So that's the problem. So any cardiologist who is treating a patient who might be at risk for left ventricular thrombosis will do everything they can to make sure that the person does not get a clot. And so stratification of risk, kind of figuring out which patient is at high risk and which patient is not at high risk, is a very key part of the treatment protocol. And currently in the United States and most other places, they use basically two key kind of metrics or factors to decide whether somebody is at high risk for clot formation or not. And one is that the person should have a certain type of a heart attack. It's called an ST elevated myocardial infarction, STEMI. And just again, in common language, this just means it's a massive heart attack. It's a heart attack that is connected with the blockage of a certain artery in the coronary circulation. So, and there's about, in the US alone, there's about 250,000 of these per year. So that's factor number one, that somebody should have had a STEMI. And then the other thing is that person's ejection fraction should be less than 30%. If a person satisfies these two criteria, they're considered high risk for LV thrombosis, and they are usually put on a very aggressive regimen of antithrombotic therapy, and this is called triple therapy. It consists of anticoagulation, antiplatelets, and also blood thinners. However, it turns out that ejection fraction, this EF less than 30% ejection fraction, turns out to be a very poor predictor of risk. And there's multiple studies that have been done to show that, in fact, ejection fraction does not accurately predict thrombus formation. And I'll show you some data here, and this data is central to kind of our work. So what we did when we started working with these group of cardiologists, we went into the database, the patient database at Johns Hopkins Hospital, and we selected 75 patients out of that, 75 patients for whom we had very good quality data, imaging data of the heart and other kind of health parameters. And we picked this cohort such that we had 3 cohorts of 25 patients each. One group was the normal group, no problems with their hearts. And then we had 2 groups of 25 each. One was what I'm going to call the LVT group. And this is a group that actually showed a left ventricular thrombosis in their left ventricle. So these are people with a clot. And then we also found 25 other patients whose hearts were seemingly as badly compromised. So on the y-axis is the ejection fraction. So we found patients whose ejection fractions were as low as those of the LVT group, but these patients did not have a left ventricular thrombosis. So notice, first of all, that all the normal patients are all above 50%. So that's what we would expect. But interestingly, if you look at these 2 groups, the LVT group and the cardiomyopathy, the CMP group, their average ejection fraction is about the same. It's about 25% or so, below 30 for both these groups. But one group has a left ventricular thrombosis and the other one does not. So that clearly shows that ejection fraction by itself would not be able to differentiate between these 2 groups at all. It would have a very low diagnostic accuracy in predicting who's at risk. And the question is that this, the risk, there is also a risk to prescribing this therapy, this antithrombotic therapy to somebody who doesn't need it, because it turns out that if you look at the data, this is just our data, but if you look at other data and other publications, the estimate is that only 1 out of 10 people who actually receive this therapy require this therapy. So this therapy is being overprescribed by a factor of 10. And the issue here is that for people who take this antithrombotic therapy, they have a very high risk of bleeding incidence. And many of these patients, almost 50% of the patients on this antithrombotic therapy are at high risk of bleeding, and they might have gastrointestinal bleeding or other types of fairly serious bleeding incidents. So it is very, very important that we figure out more accurate ways of stratifying the risk between these 2 groups. We really want to figure out more precisely which patient should get the antithrombotic therapy and who should not. So this was kind of the task that was given to us by our cardiology colleagues. They said, we have this ejection fraction which doesn't really work very well, and we would like you to come up with something better based on your understanding of computational, based on your understanding of the fluid dynamics. So that was the task that we set ourselves for. And the basic idea when we started this project was that basically there are 3 aspects that we had to deal with. There's, of course, the computational hemodynamics and blood flow, which we kind of know what to do. We know how to simulate. But then we had to deal with the coagulation biochemistry and also patient physiology, right? We had to get data from patients and be able to apply that data, be able to take that as input and then come up with some predictions that could be used to improve the stratification of these kinds of patients. So let me kind of explain a little bit about the process of the modeling process itself. The simulations are all performed using our immersed boundary code. I won't spend too much time on this, but it's a Cartesian grid immersed boundary code. We've spent a lot of time and effort over the last 20 years developing and improving this code. Basically, all the simulations are done on a Cartesian mesh. So here's the heart inside a Cartesian mesh. The mesh is actually much finer. It has this simulation is almost 28 million mesh points. And these are the kind of results that we get. So this is a simulation carried out of the left side of the heart, you can see the kind of beautiful and very complex flow that is created in the left ventricle in every heartbeat. So this is what's happening in your heart in every heartbeat. All these vortices are being created, all this beautiful flow is created, and then all this flow gets ejected out into the aorta and the rest of the body. So flow simulation is pretty straightforward using this. And of course, we can also do lots of other things like compressible flow simulations, acoustics, convection diffusion, fluid structure interaction, and I'll show a little bit of some of these things as I go along. And by the way, this code that we have developed, this Vicar 3D code, can do a lot of different things. So for students out there, thought this would be cool to see all the different things that we are doing with the code. We're looking at insect flight, we're looking at energy harvesting, we're looking at chemical engineering problems like mixing in micro mixers, aeroelastic wing flutter, and then turbulent boundary layers. So these are all being simulated. Schooling of fish. What happens when two fish swim next to each other? Do they get some hydrodynamic benefits from that? So these are just a small sample of some of the projects that we have done with this code. But so simulation aside, now the next thing is the biochemistry. And this is kind of interesting. I was never really interested in chemistry when I was a student. Really didn't care much about chemistry, but I've learned to like chemistry since I've been working on this project. So I'll just very quickly explain the chemistry of coagulation. Because I think hopefully you'll all find it very interesting. So here's what happens if there's a tissue and the tissue gets damaged. So let's say you cut yourself in your finger. So here is what happens. Here's the process that leads to the formation of a clot. As soon as the tissue is damaged, it immediately releases a chemical called the tissue factor, TF. And the TF initiates a whole cascade of chemical reactions. So the tissue factor release goes through a whole cascade, and in the end, it produces a chemical called thrombin. And thrombin now starts to kind of move into the bloodstream, and the thrombin initiates two things. It initiates the next stage in the coagulation process. Thrombin, number one, it activates the platelets. And what does that mean, activate platelets? Well, in a normal state, when you're uninjured, your platelets look like ellipsoidal in shape. They're nicely smooth shaped, ellipsoidal. They slip past each other very nicely. They don't stick with each other. But when a platelet encounters thrombin, it activates and it changes its shape. It grows all these arms and legs, and it wants to hold on to other things. It becomes very sticky. And secondly, the thrombin also converts fibrinogen into fibrin. It takes small chain molecules and ties them together to make them long chain molecules. So thrombin is the key part of the coagulation cascade because it creates the brick and the mortar for the formation of the clot. So that's the whole process. So we wanted to kind of simulate this process to really see how the clot formation is connected with the fluid mechanics. So we took these chemical reactions. You can kind of, again, this is like combustion chemistry. You can come up with as complicated or as simple a model as you want. We decided to go with kind of a 18 species kind of a reaction chemistry. And we coupled this with the Navier-Stokes simulation. So this is the convection diffusion reaction equation that we can actually solve simultaneously with the fluid mechanics. So this is the way we model the coagulation. And these are the results. So this is the patient with a very severe heart attack. You can actually see that this part of the wall, the lower left part of the wall, is very damaged. It doesn't move a whole lot. It's completely static. In a normal heart, the entire wall needs to be moving very nicely and smoothly, but you can see that this wall is not moving well at all. So this is kind of the vortex structure that you see that form in the left ventricle of this person with a fairly severe kind of myocardial infarction. And again, you see that there's flow coming in from the left atrium, and then the flow goes out to the aorta. So this is kind of the very fundamental kind of a view of how the flow looks like. Now, in addition to flow simulations, for the first time, our group was the first one to do this. We can also start to look at kind of the concentration of the various biochemicals that are key in the thrombin in the coagulation cascade. And again, here we are showing vorticity. The little dots that you see think of them as blood cells that are circulating inside the left ventricle. And then these isosurfaces that you see on the lower left, these are isosurfaces of thrombin concentration. And you can see that actually thrombin does accumulate preferentially in two locations in this particular person's heart. One is near the apex, and the other one is kind of near this little aneurysm that is forming in the left ventricle. So presumably our model is trying to predict that these are the locations where most likely a clot would start to form. And the other thing that I was telling you about was this nice sweeping flow that you see. So usually in a normal heart, the flow comes down on the right side of the wall and then sweeps around the ventricle and then goes out through the aorta. But in this case, you can see that because the ejection fraction is not high enough, the blood doesn't get to sweep all the way to the apex of the heart. It kind of dies before the jet gets to the apex. So we're just looking at some mixing and washout kind of, we're looking at some passive scalar. And you can see that the passive scalar is not able to wash out the apex. So these are some of the kind of overall qualitative features that you see in the simulation. And so we started to generate these results, and we went back to the cardiologist and we said, okay, we are starting to see all this information. And it's very interesting working with cardiologists, kind of somewhat different from us many of us are interested in fundamental science, and we are taken in by the beauty of just the fundamental science. But these cardiologists and physicians, they only get impressed if you can show them something that will help their patients. So they looked at this and said, this is all fine, but what do we do with this data? This we can't really use this to do something practical and useful for our patients. So come tell us something practical. Tell us something that we could do, change the way we treat our patients, or change the way we diagnose our patients. So we kind of went back to the drawing board and started looking at what kind of metrics could we obtain from these simulations. What kind of metrics could be obtained from patient analysis that could help us come up with a better stratification of risk than the ejection fraction itself? So one thing that we thought about was that, the more time that the flow spends near the damaged wall, the more chances of clot formation. Because if the residence time of the flow is large, that means there's more stagnation of the flow near a certain region. That means the risk should be higher. And so we did some initial studies to show that actually this near wall residence time, this NWRT, this factor, the amount of time being spent by the flow near the wall, actually does have a very good correlation with the thrombin concentration. So as you can see, this is a correlation from like a dozen simulations, and the thrombin concentration and the near wall residence time are actually quite well correlated. And what this meant was that we could proceed further with our analysis without having to worry about chemistry. The fluid dynamics is actually driving everything. The chemistry is not that critical. So that was good news. So we said, okay, we went back to the cardiologist and said, okay, we found this new parameter called near wall residence time. And if you can measure near wall residence time, then that can tell us something about the risk. So this curve tells you the risk of, in some sense, this is the risk curve, and the risk curve really takes off if the near wall residence time is above about one second. If the flow is spending more than 1 second near the wall, then your risk goes up very, very rapidly. So we said, okay, this could be something. But again, the cardiologists basically said that this near wall residence time is almost impossible for them to obtain from their echocardiograms or other types of imaging, clinical imaging that is being used. So we had to again go back and start thinking about something even simpler. And after looking at and this is the beauty, I really enjoyed this process of working with the cardiologists, because they really forced us to think simple. I think many times we think really complicated. We think complicated is better, but actually this was one instance where we were forced to think simple, and actually that was what led to what was the breakthrough in this research. So in looking at this data and looking at some of these patient simulations that we did, what we realized was that there is a kind of a very simple metric that was staring us in our face. And this metric was that this jet that comes from the left atrium into the ventricle, in this particular patient, this jet never makes it to the apex of the ventricle. That means that the ventricle will never get washed out. And so if the jet does not reach the apex, that is high risk. And conversely, if the jet reaches the apex, then that person's ventricle is going to be washed out very nicely, and that would be low risk. So we said, so this is an easy metric. We need to just measure the length of the jet that is coming in and compare it to the length of the ventricle, and that ratio should tell us the risk. And it turns out that the length of the jet, the length of the ventricle is very easy. This is obtained in almost every cardiac exam. The length of the ventricle is reported very, very quick, it's reported automatically in the examination. The length of the jet, it turns out, is also available. So here is a typical echocardiogram of a patient. And this is, think of this as the velocity versus time, measured at this red circle. Wherever this red circle is on the left plot, that is where this velocity is. And you can see actually hearts tend to be biphasic. There's a two-phase filling of the left ventricle. You have the E wave, which is the major filling, and then you have the A wave, which also adds a little bit more. So the E wave is the dominant wave in the left ventricle. And it turns out that echocardiographic examination of a patient automatically, in most cases, generates a number called the velocity time integral, which is nothing but the area under the yellow curve. And the area under the yellow curve, in some sense, is a measure of the length of the plug of flow that comes out in the E wave. And that's, to us, that is almost analogous to the length of the jet. So after all these simulations, our idea then boiled down to the fact that there is this new metric, which all you need to do is take two things that are already measured in a current exam, the velocity time integral and the length of the left ventricle. You take the ratio of the two, and we call this ratio the E wave propagation index. And if this ratio is less than 1, then the person has an incomplete washout and high risk. If this EPI is greater than 1, then the person has very good washout or good washout, and the person should be at low risk. So this was the metric that we finally said to the cardiologist, okay, this is the metric that you should be using. And the question was, how well does this metric work out? So again, to remind you, this is the data set that we started to work with, 75 patients in 3 cohorts, and that 30% ejection fraction. Anybody below 30% would be considered high risk, and anybody above 30% would be considered low risk. And you can see that many patients who have ejection fractions less than 30% do not have left ventricular thrombosis. And so it seems like this 30% is not predicting things correctly. So we took the same data from these same patients and reformulated it to compute the E wave propagation index. And this is what this data looks like now. So you can see now that we get so 1 is the break-even point. Anybody below 1 is high risk. Anybody above 1 is low risk. Interestingly, first of all the normal patients have EPIs greater than 1. So that is great. That's good to know that normal hearts, the EPI is greater than 1. The next thing that you notice is that all the patients with left ventricular thrombosis, their EPI is less than 1. So in some sense, this is very precisely finding those who are at risk. Within this group of CMP, these are patients who did not have a left ventricular thrombosis. We found that out of these 25, 21 were correctly predicted as having higher EPI than 1. Only about 4 actually had lower EPI. And it turns out of those 4, 2 patients actually showed up with a left ventricular thrombosis in a later exam that we found out. So in fact, EPI predicts out of 25 patients, EPI predicted for 23 patients, it predicted correctly that they were not at risk or at risk for left ventricular thrombosis. And notice that this little triangle of this person who actually had a left ventricular thrombosis, despite having ejection fraction of 55%, that person is also correctly classified, because it turns out that even though that person has a high ejection fraction, that person also had a very extended left ventricle. So the left ventricle had grown to be very large. So despite a high ejection fraction, the flow was still not getting to the apex of that ventricle. So this EPI very nicely kind of accounts for not only the fluid dynamics, but also kind of the morphology and the physiology of the person's heart. So we did this work in 2017 when we published this in 2017, and then we kind of stopped this work because my cardiology colleagues who were working with me moved away to other institutions. And so we kind of could not continue this, but very recently, last year, a very interesting study was published by a group from Denmark. It's a group of cardiologists who took our EPI and they applied it to a patient data set, to about a cohort of about 364 patients who all had this acute myocardial infarction, the STEMI. And long story short, this is basically what you're seeing on the right-hand side is the typical kind of receiver operator characteristic of a diagnostic, any kind of a diagnostic metric. On the x-axis is specificity, on the y-axis is sensitivity. So specificity is, kind of positive predictive rate, and sensitivity is negative predictive rate. How well are you correctly predicting somebody who has the problem or doesn't have the problem? The 45-degree line is corresponding to a coin toss. So if somebody were to just randomly guess, this green horizontal, the 45-degree line corresponds to a coin toss. And the higher you are above this coin toss line, the better you are. So just for comparison, the ejection fraction is kind of this orange curve. And then the EPI is the blue curve from this data. So you can see that, in fact, there is tremendous improvement in going from left ventricular ejection fraction to the EPI. So EPI turns out in the study to have a specificity of 97%, which is almost perfect. So EPI has been found to be very, very good at ruling out LVT, which actually is the more important thing than ruling in. So, being able to predict who is not going to be at risk for EPI is more important because it's being over predicted right now. And then more recently, actually, there was an editorial published in the International Journal of Cardiology that actually, that actually kind of pointed out the huge potential of the use of EPI for better diagnosis of patients. So we were quite happy to see that work that started off in our group as a fundamental kind of fluid dynamics exercise has reached to a point where there's an editorial in the Journal of Cardiology asking cardiology people all over the world to actually try out this index. And I'm very hopeful that more groups are going to jump in and start looking at this EPI, and hopefully this will become a real diagnostic modality that will be used by people around the world, and maybe it'll save some lives and improve the treatment and diagnosis of patients all over the world. So that's kind of our hope. So this is kind of the first part of the talk, and I'm going to quickly go to the next part and take the next 10 minutes to tell you about a completely different project, but uses the same code and same computational methodology, which is looking at the biophysics of kind of flight tone-based communication in mosquitoes. Very, very interesting idea. And of course, we all come from India. India, mosquitoes are a real bane, produce all kinds of diseases like malaria, chikungunya, and dengue fever, and all that. So we've been working over the last 4 or 5 years to try and kind of understand more about the biomechanics of mosquitoes and trying to figure out how we can maybe do something that can affect kind of infection rates and in the life cycle of these vectors. If we can do something to these mosquitoes and the life cycle, maybe we can have an impact on reducing these mosquito-borne diseases. So it turns out that this picture I'm showing on the right-hand side is the male and the female of a mosquito. And it turns out the male has a very, very, very sensitive antenna. The antenna is very sensitive to sound. And it turns out the reason for that is that mosquitoes are using their flapping wing sound, the buzzing sound that we hear from mosquitoes. While we might be irritated by it, actually it turns out that mosquitoes are using the sound of their wings to communicate with each other. Males and females communicate with each other by using the sound of their wings. And mosquitoes are therefore very, very sensitive to sound. So the antenna of a mosquito can measure about 2 nanometers of deflection from sound. So that's how sensitive the mosquito antenna is to sound. So sound is critical to these, the buzzing sound is critical to these insects. That is how a male finds a female, and then they mate and they produce thousands of eggs. And if one could figure out how to interfere with this communication, you could reduce the reproduction rates of these vectors. And it turns out that the communication between males and female mosquitoes is very complex. On the bottom right, you're seeing what happens if you take a male mosquito and bring it closer to a female. The blue is the male and the red is the blue is the sound of the male and the red is the sound of the female. And it turns out that the way the communication works is that we bring these mosquitoes together closer, they actually synchronize their frequency to indicate interest in each other. So that's how they determine kind of whether you are the same species, whether the other mosquito is the same species, etc. So it's a very intricate kind of a musical dance that happens between male and female mosquitoes. So very, very interesting from a kind of animal physiology and behavior point of view. But we were kind of interested more in the aeroacoustics part. How is the sound created? How do the wings create the sound? And if we could understand something more about it, maybe we can do something about trying to interfere with the communication. So here were some of the questions, and I do want to kind of not go too far over my time, so I'll try to wrap this up fairly quickly. So on the right hand side is a video, high-speed video that we have taken of these mosquitoes in flight. And this is kind of swarming flight. So this is a bunch of mosquitoes, males and females, and this is typically what they're doing. They're swarming around, and their males are trying to find females and trying to mate with them. So the question that we were interested in was that how is the sound being produced by the flapping wings? And then can we exploit this to understand this understanding to develop new approaches for controlling mosquito populations? So for instance, one simple idea that we have pursued is that what if you introduce sound, artificial sound, into a region where mosquitoes are swarming? Can we use artificial sound of the right frequencies to be able to interfere with the communication? And then it turns out that there's some other things we can learn. Maybe we know that drones, for instance, all the drones that we make are very noisy. Could we learn something from insect flight, from the flight of these mosquitoes, that will help us to build drones that are quieter, that don't make this immense sound that almost all the drones do? And what we did was we took a comparative approach of comparing two insects. So a mosquito, which makes a lot of sound, and a very comparable insect, which has the same size, but does not make wing tone sounds, which is a fruit fly. And a fruit fly has been used very, very extensively in all kinds of research on genetics, but also in aerodynamics of flapping flight. So I'll show you some data of comparison between these two animals and show you something very interesting that comes out from this. So what we do is we take kinematics from various sources, from our own videos and also from other researchers. So what we can do is we can build models of the wing flapping. And this is kind of, on the left-hand side, you can see the movement of the wing and the vortex structures being generated by the wing. So this is being done using a direct numerical simulation, again, using our immersed boundary solver. And then on the right-hand side, you see the lift, drag, and side force that is generated by the wing. So the wing is generating lift force, drag force, and a side force. So that's going to turn out to be very crucial. And then also, this is the expended power. So this is how much power in microwatts. So this is micronewtons, and this is microwatts. This is how much power is being expended by the movement of the wings. And so force generation and power expenditure, those are the ways in which we try to understand kind of the mechanics and energetics of flight, and especially for flapping flight. So the next step now is that after we have the simulation, we have to compute the sound. How do we compute the sound? Well, we can use what is called the aeroacoustic analogy, which uses the Fox-William-Hawkins equation. And there's a formulation it's called the Bretner-Farasat formulation. And basically what it does is it connects the acoustic pressure directly to the forces on the pressure on the wing itself. So without again getting into details, if you know these forces on the wings, then you can use the forces as the input to this model of aeroacoustic sound and be able to generate the sound that is being produced by the flow. And all I can tell you is that very quickly that this method actually works really well. Here are some measurements of sounds from a mosquito wing done by somebody at Cornell. And then here is our comparison from our simulations. And you can see the colored lines are our simulations. The dashed line are the experiments. And we actually match quite well in terms of intensity, sound velocity level as a function of distance. So we have very good validation that our predictions are very good. And so now we can go ahead and calculate the sound. And sound tends to be, it turns out that sound generation is highly directional. So sound is produced in a very directional manner. And on the lower left, you're seeing actually the directivity of sound. And this is kind of interesting. You're seeing if you see the insect orientation, the orientation of the mosquito, the sound that is being produced by the mosquito is actually kind of almost ahead and behind. And one of the things is that if you are actually trying to communicate, one mosquito is trying to communicate with another mosquito that it is chasing, then directing the sound forward is a very, very useful thing. You don't want the sound to be directed away from the person that you're trying to communicate with. When we speak to a person, we turn towards them, right? So this is something similar that's kind of happening naturally in these mosquitoes, is that the sound that is generated, the buzzing sound that's generated by their wings, is naturally directed forward in the forward direction, which is much more conducive to kind of this acoustic communication. So that's kind of very interesting. And now we can do this comparative analysis. On the left-hand side is the mosquito wing, and on the right-hand side is the fruit fly wing. And on the middle is the table that shows you kind of the vital kind of differences between the two. So first of all, both insects have approximately the same wingspan, about 2.7, 2.8 millimeters. They have very different wing beat frequencies. The mosquitoes are flapping at about 700 hertz, whereas the fruit fly flaps at around 200 hertz. The wing area is also, the aspect ratio of the wing RW is also very different. Mosquitoes have very long, slender wings, whereas as you can see in this picture also, fruit flies have almost like an elliptical wing. It's a very stubby, low aspect ratio wing. And also the stroke angle for mosquitoes, it's a very short stroke angle, whereas for fruit flies, it's almost 150-degree stroke angle. Interestingly, though, despite all these differences, the tip velocity of both these wings is approximately the same, about 5 meters per second. So despite all these differences, the two wings are kind of producing the same kind of tip velocity. And that's important because ultimately the total amount of lift that is being generated is somewhat correlated with the tip velocity. And since these two insects are about the same size and same weight, they ultimately need to produce the same amount of total lift to be able to keep themselves hovering in the air. So so this is kind of the punchline, kind of the results from our simulation. And there's a lot of data out here. So let me just take you over this data. So first of all, look at this figure itself. This figure compares the sound intensity per unit mass of the insect. So we normalize the fruit fly and mosquito to exactly the same mass. So the red is the sound intensity created by the mosquito, and the green is the sound intensity created by the fruit fly. And it turns out that mosquitoes, pound for pound, per unit weight, the mosquitoes are producing about 3.5 times more sound than a fruit fly. So mosquitoes are very, very good at producing high intensity sound. The sound is also for the mosquito is directed more towards the forward direction than a fruit fly. The fruit fly sound, you can see the green lobes, they're pretty much located up and down because fruit flies are not using their sound for communication. Fruit flies are daytime flyers and they don't mate. They don't find their mates while in flight. They actually land on a surface and they find their mates by walking over to a male walks over to a female. So acoustic communication has no relevance to to fruit flies. So it's very interesting that mosquitoes rely on acoustic communication, and they are very, very different and much more effective in producing the sound. But I do want to point out this final column, final row in this table, which is the flight efficiency, is that when mosquitoes are trying to produce sound, are they compromising their flight efficiency? Are they bad flyers compared to are they less efficient flyers compared to fruit flies? Because the mosquitoes are trying to do two things now. They're trying to optimize their flight and the sound that they're trying to maximize the sound. And it turns out that the specific power, which is the power per unit weight used for flight, is almost exactly the same. So basically, it turns out that mosquitoes are better at producing sound, more intense sound, sound directivity is better for communication, and through evolution, they have come up with a movement kinematics that does not compromise their flight efficiency. So it's a very interesting example of how evolution can allow for kind of multi-variable optimization in an animal. So mosquitoes need to communicate with sound. So they have actually developed a very, very different kinematics, wing kinematics, that allows them to do that without becoming less efficient. And then, kind of connecting this back to engineering. So if we look at kind of what can we learn from this nature and apply to engineering systems, I found this very fascinating kind of work from the 1930s. So if I look at the mosquito as a small flying vehicle, it's a very loud flying vehicle. It has high aspect ratio wings. It has very high frequency. It has a much smaller wetted area of the wings, whereas the fruit fly is good at quiet flight, and it has low aspect ratio of wings. It has low frequency of flapping. It has a much larger wetted area. So in some sense, that's the difference between loud flight and quiet flight. And here's this paper, beautiful paper from 1949, where they tried to reduce the sound from a propeller of an aircraft, and look at what the high noise propeller looks like, and look at what the low noise propeller looks like. Almost perfectly, this propeller looks like a mosquito wing, and this propeller looks like a fruit fly wing. So the basic idea that these researchers back in the 1940s used was exactly the same: reduce the frequency, increase the wetted area, and when you do that, you can reduce the sound by almost 15 dBs. So 15 to 20 dB reduction in the sound comes from kind of the same. So in some sense, the mosquitoes and fruit flies and evolution has figured out something that our NASA engineers figured out back in the 1940s. So again, there's some very interesting things one could learn about bio-inspired design from this. So I thought I'll end right there and put up my acknowledgements. All the nice people I've worked with. A lot of this work has been done by my colleague Jung-Hee Seo. He's the one who's done a lot of these simulations. I've collaborated with a bunch of cardiologists, Richard George and Thura Abd, and then my graduate student Shantanu has also contributed to the simulations of thrombosis. Mosquito buzz, we are working with a bunch of biologists, Tyson Hedrick at UNC Chapel Hill, and Lionel and Gabriella from Gibson from University of Greenwich. So I'll stop right here. I think I've gone a little bit over time, but I'll be very happy to stick around and take any questions. Thank you.
Thank you, Professor Mittal, for a very interesting talk. Two very nice examples from biofluid mechanics. I'm sure there are a lot of questions from the audience. I hope you'll be able to answer those. Yeah, we can start with the Richie Garg.
Good evening. Thank you for the wonderful talk. I wanted to ask about mechanical heart valves and stents. Like, are these effective ways of reducing coagulation? Like, yeah.
Yeah. So mechanical heart valves are, they are put in for a person whose heart valve is defective. And many times the defect in the heart valve, in the native heart valve, could be connected itself with thrombosis. So So in some sense, mechanical heart valve is a solution to thrombosis. It's a solution to something that, to some kind of thrombosis in the heart of a person. Do they themselves kind of reduce thrombosis? They could. Again, if a native heart valve is not functioning properly, it becomes more prone to thrombosis, and replacing it with a mechanical heart valve can reduce that. But I have to point out that mechanical heart valves themselves are prone to thrombosis. So whenever any foreign body is introduced into our bodies, there is kind of a thrombolytic kind of reaction to that, and so the surfaces of stents and metallic valves are themselves prone to thrombosis. So usually anybody with a mechanical heart valve will be put on a regimen of antithrombotic therapy for the rest of their lives to reduce thrombus formation. In terms of stents are more kind of a downstream solution to somebody who has had clot formation and blockages in an artery. The stent tries to keep the artery open. There are things called drug-eluting stents, and the drug-eluting stents, what they're able to do is they're able to secrete a little bit of antithrombotic kind of chemicals from the stent itself, and that can reduce to thrombus formation.
Thank you.
Yash Nandola.
Good evening, sir. Can you tell something more about the energy harvesters that you showed in one of the slides?
Yeah, so that's a whole seminar in itself. So energy harvest. So what we are trying to do is we are trying to use flow-induced flutter as a way to harvest energy from the fluid. Fluid could be wind, or it could be kind of water flow. And again, we've used the same immersed boundary code. I had a graduate student and a postdoc who worked on this project over the last 5-7 years. And we showed that, in fact, you can harvest energy very easily if you have a membrane and the membrane has piezoelectric material on it. Then as the membrane starts to flutter, the piezoelectric material kind of deforms, and that deformation can be converted into electrical energy, and you can extract that energy. In fact, we took this whole idea and we actually made a prototype weather sensor, which actually was powered by flow-induced flutter of a piezoelectric membrane. We put it on the terrace of one of our buildings, and we showed that, in fact, the sensor could continue to work forever just by harvesting the energy from the piezoelectric membrane itself. So if you're interested, there's about half a dozen papers that we have published on this topic that you can find on my website. So if you're interested, send me an email and I can point you to those, or you can find them yourself on our website.
Okay, sir, sure. Thank you very much.
Deepanjan.
Hello.
Hi.
Yeah, I have two questions. One is that you showed a comparison between the left ventricle thrombosis and the cardiomyopathy. So now let's say if someone has a problem in the valve itself, because of which the velocity of the blood that is coming will be different. So in that case, can EPI give the difference between whether it's a thrombosis or whether it's a valve issue? That's one question. And the second question I have is echocardiogram is a 2D imaging. So when you are measuring that EPI from the echocardiogram, sometimes it is possible that the blood clot is in a different, like in the third dimension, it's not capturing properly in the echocardiogram. So in that case, can EPI give a accurate result?
So the first question is that, can EPI differentiate between, I think you said, between a valve problem and a thrombosis problem. So first of all, valve problems are usually, it's relatively easy to to diagnose a problem with a valve, because the echocardiograph imaging actually shows the valve movement very nicely. And I showed that, if you remember, I showed the echocardiogram, which showed the valve movement. So valve problems themselves are diagnosed in a completely different way. Now, what EPI can still do is that it can tell a cardiologist that if somebody has a valve problem, is that valve problem going to cause thrombosis or not? And that is what EPI can predict. So it's not there to predict whether a person has a valve problem. That is diagnosed by something else. But should this person go on antithrombotic therapy? Are they at high risk for thrombosis? That is something that EPI can predict. So I think that's your first question. The second question, kind of the 2D versus 3D, absolutely. I think there's certainly, echocardiogram. Actually, the echocardiographic imaging is actually kind of the final plot that we get is 1D. It's at one point. We are getting a point measurement. You can also get M mode, which is a line measurement. But yeah, of course, these are kind of approximations. All of these measurements have certain level of uncertainties and errors. One could go to 3D imaging. There's a lot of 3D echocardiography that's been developed. So eventually, I think some of those details could be removed. But I think the reality is that in 99% of the world, 3D echocardiography is never going to be used anytime in the near future for diagnosis. You need to provide cardiologists with tools that are easy, ready, and currently available. So I think despite kind of my feeling is that, and that's kind of the feeling of the cardiologist also, is that the simplicity of this metric and its improved accuracy is those are the two things that are key. It needs to be simple and it needs to be significantly better than the state of the art. As long as you have that, you have a very good diagnostic kind of capability. Hopefully 10 years from now, when 3D imaging becomes more and more prevalent, maybe this EPI could be extended towards 3D imaging.
Thank you.
Namrata?
So both Sanjay and I have questions. I'll allow Sanjay to ask his question first. This is Sanjay Sane.
I just had a comment actually about Drosophila singing to its mates. Fruit flies do actually sing to their mates. It's a pretty well worked out system of mating. So what they do is when they approach females, maybe a few body lengths from them on the surface, they will pull out one wing, just one wing.
Tapping.
Yeah, and what they do is they play a little courtship song.
Mm-hmm.
And this is, of course, a short-range song. It doesn't travel over long distances. It's a short-range song, but they actually play a song. And the song is how the female knows whether the male is of her species or not. And they also do a little dance, but that's a separate issue. Right. But this is, so, what we see in Drosophila is a short-range song. And in mosquitoes, I think it goes over a much longer range.
Right.
Because they are operating under very low light levels. And so the only real way they can, so they can't see their mate. They have to sense the mate at a distance.
Yeah. Hi, Sanjay. Good to have you here in the seminar.
Yeah. Seminar.
So yeah, absolutely. I kind of, I think the key difference is that mosquitoes are solving flight and acoustics at the same time. Mm-hmm. And the fruit flies have figured out that they don't need to solve it simultaneously because they are daytime kind of flyers. So you're absolutely right. They land on the surface and they tap their wing, and the wing tapping is the sound that they produce. So yeah, it's very interestingly different.
Yeah.
I had a question related to your heart, the heart flow dynamics part of it. So actually, I have a two-part question. One is related to, I didn't get the details of the new metric that you proposed. I was wondering how similar it is to the RRT, the relative residence time, which is a metric that is used in most of atherosclerosis literature. And the second part of my question is, how much deformation is there in the thrombus during a given cardiac cycle?
So RRT is very similar to that near wall residence time that I showed earlier. So it turns out if near wall residence time would be a good metric to predict thrombosis risk. The only problem is that that metric cannot be measured easily given current limitations in imaging protocols. Echocardiography is it's high resolution in time but fairly low resolution in space. And especially near the moving wall, the resolution is almost zero. There's very little resolution of the fluid dynamics near the moving wall of the left ventricle. And that's where the near wall residence time would have to be estimated from the echocardiogram. So the issue is not that the RRT or near wall residence time would not be good metrics. The problem is that they cannot be obtained from imaging protocols. So I think that's the kind of big difference. The EPI index is kind of I think it's a surrogate for the fact that EPI also is predicting the same thing that near wall residence time predicts. Implies that the EPI is some kind of a surrogate measure of near wall residence time. And in fact, in our paper, we have shown that the two actually are fairly highly correlated. So EPI is nothing but a more easily, a clinically available and obtainable kind of metric that replaces the near wall residence time or the RRT. The second question, I'm sorry, could you repeat your second question?
Yeah, no, this is good to know because I'll go back and check your results. My second question was related to how much deformation is actually present in the thrombus during a given cardiac cycle.
Good question. And we don't know the answer to that very well. So these echocardiograms, these thrombi show up as, they call them smoky signals on an echocardiogram. They show up as smoke, almost like smoke, very, very fuzzy. It is well known that clots can be red blood cell rich clots. So you can have white clots, which are white blood cell rich clots. You can have clots that are highly mobile and they sway back and forth almost like trees in a wind. Sure. Or you can have clots that are very, very kind of solid and rigid, and they are very nicely anchored to the wall. You can have clots that are very, very flat and kind of very flat along the wall, or you can have clots that are very, very much protruding out of the wall. So very, very large variety of morphologies of these clots, and deformation is something that I don't think I've seen any studies that really in left ventricle. There's a lot of studies on clots in all kinds of the lesions in arteries, etc., and kind of looking at the stability of those lesions. I have not seen similar studies or data for the left ventricular thrombus. My guess is that new clots tend to be a lot more mobile, a lot more deformable. And old clots, and I've seen old clots, by the way, I've seen clots extracted from hearts, kind of a difficult thing to see, but some of them are massive and they almost look like balloons of blood. Almost right. The consistency of
I mentioned this was in the context of mechanobiology, because a lot of your signaling that you would recruit in your models would be related to the kind of deformations which are present. So I was sort of alluding to that context. But thank you. I'll go through your papers. Thanks.
Anand Suresh?
Yeah, Rajat, excellent talk, excellent bioengineering work, both your case studies. I have a question about your comparative analysis of fruit fly and mosquito. There must be some scaling laws that capture these, Steve Vogel has done a lot of work on comparative biomechanics. So that is one thing. There must be some scaling laws relating the frequency and the wing aspect ratio and sound intensity. The other is I didn't get how your understanding now can be used to, kind of make it difficult for mosquitoes to see each other.
Yeah, so excellent question. So indeed, there is a scaling law. There's a separate paper, and again, because shortage of time, I couldn't get into this. We've actually taken mosquitoes and artificially kind of changed their flapping frequency. So it turns out the mosquitoes are different frequency, different species, you have Aedes, you have the malaria causing mosquito, you have like many varieties of mosquitoes. The flapping frequencies of mosquitoes range all the way from about 300 hertz on the lower side all the way to about 1200 hertz for some of the male Aedes mosquitoes. So wide range of frequencies. And so because of that, we looked at frequency as a key parameter in these mosquitoes. All of them have frequencies that are higher than almost all comparable insects. And it turns out that in terms of scaling, frequency is the key. So the sound intensity is scaling with the square of the frequency. Everything else being the same, it's the frequency is driving everything. But then what happens is that since the mosquitoes have a higher frequency because they want to produce more sound, they have to start adjusting other things in order to have efficient aerodynamics. And the other things that they adjust is that they end up having long, slender wings, and they end up having a short, very shallow stroke. So then we have looked at the scaling of this with stroke angle. We have looked at the scaling of this with kind of the aspect ratio of the wing. And it turns out that there are some very nice scaling laws that come out. So there's an entire paper that kind of looks at the scaling issues. The second part about control, this is very interesting. And actually, it's very interesting. We actually did the experiment on control of mosquitoes way before we did the simulations. I had a couple of really smart undergraduates who were looking for a project. We got a little bit of funding from the Malaria Institute at Johns Hopkins. And I was always, and Sanjay will know this, that these mosquitoes, all these insects have a resonance resonance mechanism that drives their wing flapping. So the thorax is kind of a resonance box. And so I was always thinking that if you have a phenomena resonance, if you can feed back the same frequency, you can drive that resonance to very large magnitudes, and that should make flight uncomfortable for these insects. If you try to kind of resonate their thoracic, kind of the resonance chamber. So I was always interested in, okay, if we introduce the frequency of flapping to these insects, what does it do? And it is unbelievable that we had a box of these mosquitoes that you saw in flight. We were showing a whole swarm. If we actually introduce sound at the right frequency, which matches their frequency, half of the mosquitoes fall on the ground. They become completely overwhelmed. And initially we thought that this is a mechanical response, but more and more it's clear to us that it is more of a neuromechanical overload. We are overloading their acoustic system. Their antenna is very highly sensitive to the flapping frequencies of the females. And if you load them with that sound, it's basically an acoustic overload for them. And it becomes very difficult. It's somebody like having loudspeakers right next to your ears. It becomes very difficult to operate, right? That it kind of overwhelms everything. So we did see that kind of interaction. We also saw that if you took pregnant mosquito females and you expose them to long duration of low intensity sound at the frequency of their flapping, it reduced the number of eggs that were produced by these females, the number of viable eggs that were hatched. Now, these were very small cohort studies, so we haven't published. There's one study that just came out where we looked at the sound intensity in scientific reports. But the egg hatching study, we need more data before we can really kind of come out and really be confident about that. But those are the kind of avenues of really trying to take this research and trying to use that to affect malaria control and disease control. One is make it difficult to find each other, the mates. The other one is make it difficult for them to fly around. And third thing is reduce the number of viable eggs that are being produced by these animals.
Right. That will be really nice translation. All the best. Thank you.
We have Venkatesan.
Good evening, Professor Rajat Mittal. I have one quick question. You were discussing about the sound travel by mosquito. So is it different in different media? It's in air and water, because the dengue is supposed to be by stagnant water mosquitoes.
Yeah, so obviously, sound speed and everything is very different in air and water, but this swarming is happening in the air. So even though the eggs hatch in the water and everything, adult mosquitoes are swarming in the air. So the only relevant medium to kind of look at this issue is air.
Okay. Thank you.
Mhm.
Richie, you had one more question, or?
Yes, one more question.
Yeah, please go ahead.
So it's a non-technical question. So, like, if say at academia level, when a technology is invented, for example, a portable ventilator, what
Mhm.
measures could be taken to speed up the implementation of that technology by doctors?
So that's a great question. And I've been involved at various levels in kind of commercializing technology. So first of all, one has to realize that in most cases, unless there is kind of emergency use authorization and all that, which of course during COVID has happened quite a bit, but the normal route to anything like this requires a lot of clinical trials. So you need to conduct a series of clinical trials. You need to show safety, and then you need to show efficacy, and then you need to show superiority or non-inferiority. So there are three things that you need to show for every technology: that it's safe for use, it is efficient, it actually accomplishes the purpose, and it is at least as good, if not better, than existing technology, existing solutions. So many times when you come up with any new idea, technology, that's kind of the hurdles that you have to go through in order to get to the point where you can start thinking about commercialization. So that's kind of my short answer, and I could give a very long answer on this also.
Like, with your experience related to communication with doctors, like, what were the major challenges? Yeah.
I think the major challenge is the biggest challenge is that I think there can be a kind of a communication barrier. We use different language between the medical profession and engineering, very different language. Kind of, when I say language, I mean terminology, and the way we kind of a very different way of thinking about problems. Working with physicians and cardiologists and other doctors, my tendency as a scientist and engineer is, oh, this is very interesting. This flow physics is so interesting, and for them it's completely irrelevant for the most part. They are not as fascinated by something that is just because it's interesting and cool and kind of advances fundamental science. Their immediate questions to me again and again are, okay, so what? Tell me how this is. I don't see any use of these colored fluid dynamic stuff. Tell me how this is useful. And so I think that to me has been, I've worked with doctors and physicians for over 15 years now. And I think it's still a challenge to really change my mindset and make it more aligned with their mindset. Because ultimately, I think you can only make them interested in the fundamental science if you can actually first show them the translational value of potential of what you're doing.
Thanks a lot, sir.
Mm-hmm.
Ratnesh?
Yeah. Perhaps I missed it. I just wanted to know, you said that specific power for fruit flies and mosquitoes are nearly the same, right?
Mm-hmm.
How different are their flight speeds, effectively the cost of transport?
Yeah, that's a good question. We've for mosquitoes, we have tried to do our own experiments. There's not good data available on kind of the flight speeds of mosquitoes. They can vary quite a bit. Actually, the paper that just got accepted, one of the reviewers actually asked us for that same data, and we had to go back to that reviewer and say, we really don't have fruit flies. There's a lot of data on flight speeds, etc. Fruit fly is probably the most studied flying insect in the history of kind of insect flight, I think. But mosquitoes not as much. So I think that's an interesting question. Just from our own observations, the little bit of experiments that we have done in our own lab, flight speeds of mosquitoes are somewhat comparable to those of fruit flies. I think they're a little bit slower. Again, I think this might have to do with the way they function and kind of how they feed, etc. But somewhat in the same ballpark range, if I were to guess.
Right. Thanks.
Yogendra?
Am I audible, Jayant?
Yes, you are.
Professor Mittal, let me thank you and congratulate you for a very wonderful talk about how we go about modeling insects and hearts and so on. I was just wondering, following up on what Radnesh mentioned, that in order to generate this type of power, like 25 to 30 watts per kg, I suppose that's what you showed on those tables, right? So, are you able to hear me, Professor Mittal?
Yeah.
I was just wondering, the numbers that you splashed, like 25 to 30 watts per kg, is in the same order of magnitude as what we produce as human beings. And I was just wondering how these insects, are not affected by fatigue. Which are there attempts to model fatigue and how the power might come down with each wing beat, and so on, and be able to figure out when actually they get so tired that they are unable to flap their wings? That is my question.
Yeah, so that's so it's not surprising that the flight power that we get is somewhat similar to mammalian muscle. Muscle is muscle. In fact, fruit fly muscle has been used. I have colleagues at Hopkins who use fruit flies as a surrogate for understanding cardiac muscle performance in humans. And the underlying assumption there is that ultimately insect flight muscle is fundamentally kind of similar to muscle in other animal species. So I think that part is quite is consistent. I think in terms of fatigue, that's a great question. So one of the questions that we were trying to understand was that when two males come next to each other, when two mosquito males come next to each other, studies have shown that they try to increase their frequency as a way to increase their amplitude of sound and to kind of show their own fitness. And they use that also to show fitness to other females. And one of the things that we were interested in was to see how that would increase the energy expenditure and maybe kind of increase the fatigue, decrease the time of flight. Yes. So I think that is an interesting question. And of course, we know that these animals do rest for the vast majority of the day. These animals are perched and they're resting. So I think fatigue is a problem. It's outside kind of my own area of research. Maybe Sanjay might have done more work along these lines than I have. He might be able to answer this question better than me.
Well, I'm not hearing any response from that side, but thank you. Is there something, Namrata, you want to say? Is he around or? If not, once again, let me thank you for a wonderful lecture, and I learned a lot today. And say hello to my friend Ramesh at Johns Hopkins. Thank you.
Oh, will do.
I think we have a question from Deepika.
Yes, sir. So I just wanted to know, is there exist any correlation between this API and artery blockage happening due to blood clots? Because there can exist a case where blood is reaching the farthest end, like the left ventricle of heart, but there is a blood clot in that which can be washed away by the blood. So if you can just.
So yeah. So there could be potentially a correlation between EPI and thromboembolism. Thromboembolism is a blockage of an artery because of a thrombus. In fact, the same group at Denmark that published this study, we've actually started a little collaboration with them. And one of the things that we are trying to see is that can the incidence of stroke. So stroke is kind of when a clot breaks off from the left ventricle, the most likely location it's going to go is kind of in the cerebral circulation. it's very interesting that if you look at a small particle, if you introduce a small particle in the left ventricle and you ask the question, what is the probability of where this particle is going to end up? Actually, the particle has a much higher probability of ending up in the cerebral circulation than anywhere else. So what that means is that for people who have a low EPI, that means they have a higher propensity or risk for the formation of a clot in the left ventricle. That should also correlate with people who are experiencing stroke. So what we are trying to do in this new study is correlating incidence of stroke with low EPI. We want to ask the question, if somebody has had a stroke and we go back and measure that person's EPI, will we find that the EPI is low? Because I think if we can do that, that'll be a next step in terms of, again, kind of proving that the EPI has tremendous kind of diagnostic value. So that, I think, would be a very nice correlation between EPI and subsequent downstream blockage of an artery.
Okay, thank you, sir.
There's a question from Satyajit.
Yes, sir. Hello, sir. Thank you for the wonderful talk. I have one question regarding the simulation of the left ventricle. My first question is, how important is it to go for direct numerical simulation for the ventricles? I mean, how large is the error if we, let's say, go for a LES simulation? And I'm asking this question because even the flow field can, even if the flow field can reach to a, let's say, a steady state or dynamic steady state in 1 or 2 cardiac cycles, sometimes the transport of the passive scalars, in this case there are a lot of scalars like the thrombins and all the stuff, those can take a lot of cycles to reach a dynamic steady state. So it can become very computationally expensive. So that's what my question is. So how? Yeah, thank you.
That's a great question. So it turns out, though, in our code we can actually turn on in LES the dynamic Smagorinsky model, and we can run a simulation using LES. The problem is that turning on LES does not diminish the resolution that is needed, because the resolution is being driven by the flow around the mitral valves, around the kind of the laminar boundary layers that form in other places. So even if you employ LES, this is a situation where the use of LES does not allow you to reduce the required resolution of the simulation. So in that sense, it turns out turning on LES has very little advantage in this kind of a simulation. And you're absolutely right that the flow can reach a steady state, a stationary state, in about two cycles actually.
Yes.
The second cycle is already very similar to any other subsequent cycle. But of course, thrombin calculation and accumulation and residence time and things like that require much longer simulations. In fact, we have done simulations of about 8 or 10 cycles for some of these cases to really understand the cycle to cycle kind of evolution of these chemicals. And unfortunately, there's kind of no way around that. If you want to do an accurate simulation, DNS seems to be the way to go.
Yes, sir. Thank you, sir.
Raghu?
Thanks, Rajat. That was really enjoyable. I know it's very long. I just have one quick broad question. Just to know about the heart simulations, I was just curious how you do them. Do you prescribe the walls, or do you let them deform, or how do you approach it?
Yeah, that's a great question. So all of these simulations that I showed, what we are doing is we are getting CT scan data from patients, and we segment that to get the moving wall, and we prescribe that as a moving wall in our simulations. So we are not solving the FSI problem for the wall itself. To solve for that, you need to solve the entire electromechanics problem.
Right. No, it's complicated. I understood. That's why I was just curious how it's done. So you have the input conditions for the flow and the prescribed conditions for the wall.
Yes,
great.
Exactly.
Thank you. Really enjoyed the talk. We'll talk more later. It's been a long time for you. Thank you.
No, I'm happy. Yeah, I'm happy. I really enjoyed this discussion. Happy happy to answer any other questions.
Yeah, I think there are no other questions right now. I think we can formally close the lecture. And thank you again, Rajat, for a very interesting and inspiring talk for the youngsters, I believe, and how one can translate science to application. And I think those of us who are interested in chatting a little more, we can stay on. So